Hello, my name's Chris Thanis. I'm a KMP developer. Tech support's coming out on Tuesday. On Tuesday to close that portal. Maybe. Hopefully. I don't know. Probably not. We'll see. Okay, we left off on floating point numbers. We're getting into representations. This section over here, data structures. Here, right here, we're getting into, we just did numbers with floating point and craziness. That can happen if you're not aware of some things about floating point. And we're getting into the characters. So of course we can just represent the memory characters, using ASCII or Unicode, which is like ASCII extended. So you can have pretty much any alphabet in the world available. Just adding bytes, basically adding bytes to the end instead of just having one byte. You can have 2 bytes or 3 bytes or 4 bytes, and it's very clever how they have that set up. We'll look into it, and maybe at some point you're probably going to need to if you're going to be using any 2-byte systems. So not too bad, not as gnarly as the floating point stuff, but still clever and very useful. Okay, so need to represent. Hey, do we need? Okay, we got the floating point. We got numbers. We got letters. We got characters. We got ASCII characters. American Standard. What is it? American Standard Code for Information Interchange. Oh yeah. Okay, I just want to say this. Before ASCII came along in '63, every computer company had their own system. Yes, of letters and numbers and letters and characters and symbols. And do you think they were all compatible? No. Do you think any of them were compatible? No. No, IBM had their own. It's called EPSIDIC. There was all these translation programs just for translating data from one computer system to another. Talk about vendor lock-in. You couldn't even use the same files. You couldn't even use the same data. The data had to be changed. It would come in as garbage from one system to the next. So there were companies that were set up just to do that. They're out of business when ASCII came along. They were done at that point. They was like, okay, this isn't gonna be a thing. But the EPSIDIC went along until the 90s. I was still translating files in the 80s and 90s for people as a business. EPSIDIC was one of their standards. It was easy by then. So do we need to represent something else? Okay, so we live in a representational world. These bits, like that you've seen, can mean anything, and it's just up to the cleverness of the human being and devising an algorithm that takes advantage of some property, some mathematical property like the two's complement or how the floating point stuff uses division for the bits. Okay, whatever someone can come up with when they've had too much pain of dealing with it, they'll come up with something, and these are some of the standard patterns. But you can make up your own for all this stuff. There's nothing that says that we could just have to use these. And although these are probably going to be a combination of these, and when you come right down to it, these are the basic like Lego building blocks of how you build up an idea for how the computer can deal with it. Okay, but here's the issue. So humans live in a representational world. We don't really actually live in the world. We live in representations of the world, unless we're touching it physically. Okay, that's the world we're living in. But other than that, we just have ideas about the world. And this problem of mistaking what we think of the world as the world is called the map is not the territory problem in philosophy and psychology. It's the cave. The philosopher, the prisoners in the cave, Plato's cave. It's that kind of thing. What we see is the projections on the wall of reality. We don't actually get to see actual reality. We just see because the allegory of the cave is actually your eye. We don't actually see. We're not out here in the world. We're coming through reflections, coming through the hole in our eye. Right, that's the cave, but that's being projected on the back wall of the cave, and that's what we're actually seeing. So even then, we're not actually seeing the world. And we never get to see our own face. That's the other thing too. It's interesting. Unless we have a mirror, right? And before mirrors came around, we could never see our own face. We had to trust what the people saw of us, and we didn't know. Okay, and that's the thing. So a big problem in computing is like giving metaphors for concepts that people often confuse all aspects of the metaphor for the concept that were not included in the metaphors. This is like overextending the metaphor. I was like, well, if it means this, well, then it means this too. Okay, So like if a dog goes down the street and pees on a pees on a fire hydrant, that means if you're comparing this class dog, that doesn't mean it pees on fire hydrants too. No, no, that's not what we mean. So usually, when you're using a metaphor, you do have to be careful when you're sharing it with people that the metaphor is appropriate, or you say or put limitations on it. Like you can't extend this metaphor. It's just this. It's like so you have to be super careful about using metaphors because non-technical people will extend it past and make it human out of it. It'll anthropomorphize it. It'll give it human qualities and extend it way beyond what it was initially meant. Okay. So, like for example, the desktop metaphor in a computer's desktop is not the same as a physical desktop. You can't take a pencil from the art program and start scribbling someplace else in some file somewhere, and that'll change it permanently or ruin it. So that's what I mean. You can't. It's not a physical desktop. It's just the idea of a desktop where you have folders and documents, and you're shuffling things around like you're on a real desk back in the '60s. Okay. So metaphors often break down when they extend it too far. So it's important to know what's actually happening. So these concepts, so the names of these data structures aren't actual things. They were just ideas of how to arrange bits in memory. In an algorithm to process these bits in a way that's conceptual, that we can share ideas with other people about these things. That they will also, okay, you're talking about this. Okay, you're talking about that. So the numbers and characters are the most common things that people represent in memory. So at the end of the day, it's going to be a number or a character or some color. That's just numbers, right? So if it's just a number, even if it's a sound, it's just a series of numbers describing the wave of the sound. If it's images, it's little picture elements. It's just a matrix of picture elements. If it's videos, it's a series of flat images, it's just picture elements at the end of the day, or an algorithm or some compression algorithm that compresses each frame and only uses some percentage of it, and then it has an algorithm that expands it out so you can see it and on video, which is just a series of pixels. That's all that's going on here. There's no magic. You're actually seeing memory live. You're seeing what a video terminal is. You're seeing memory live. What that's actually mapped. There's some memory someplace that's a buffer that's actually holding everything a copy of everything you see on the screen. It's actually memory being emitting colors. Really, literally, that's what it is. All right, so there's picture elements. Okay, so a string of 0, 1, 0, 1, 0, 1, 0, 1 could represent votes of people. It could represent switch settings. It could represent some kind of status from some sensor. Somebody broke in the vault, so this bit goes on. Beep 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 beep. And that means take an alarm, hit an alarm over here, which means the alarm's on. Beep 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 beep. It's completely arbitrary. What do you mean? And that's why it was like, what do you mean? It's like, well, I mean this, and it's like you're using a metaphor, right? You're starting to put a metaphor on it, and if you're not careful, that metaphor can go into areas that doesn't extend, and you just gotta be aware. This is part of the thing. The map is not the territory. It's just a label we give things to represent something else. Okay, so so common data structures. The big idea is like giving names to common ways of representing these data and these algorithms makes it easier for us to talk about, not necessarily understand, but talk about with other people what we're trying to do here. In this part of the code, we're using this thing to represent something else. Okay, that's it. So we got like numbers, characters, you got Unicode, ASCII. We got strings or arrays, which is like these strings of numbers, there's strings of values, which is basically memory. Remember when memory cell after another, that's considered an array. So big idea is arrays can represent lists of values in memory. So humans love to have lists of everything. Our customers, emails, the links and links. I got a list here. All this is one big list of, it's got indentations. It's one big long list. This document is actually just one long list of characters with symbols and numbers that all have different meanings. And there's just one big long list. Okay. And then it's just different parts have different meanings depending on how this editor or this website or this program here called Brave, takes in this document, this text, string of characters, and then interprets it in various ways that I have set up. It has a protocol that I apply my knowledge of how it does it to make it look like this. So I'm doing this. I'm putting this together, not the machine. I'm doing this. I'm telling it what to do. Okay, so it represents a list. The values are the same size and same type. So every single element or item in this list is going to be the same kind. If it's going to be all integers, it'll be all strings, it'll be all, or if it's some other like collection of objects, it'll be all the same. It's very rare that there'll be different types. It's rare. It's usually all the same, and there could be subtypes. You know, if it's you can say you can only have animals in here. Well, is a dog an animal? Yes, you can have it in there. If it's is cat an animal? Yes, but is a car an animal? No, a car's not an animal, so you can't go in there. So that kind of thing. That's it. This is a one-dimensional array. It means it just goes one after the other, and then you have a two-dimensional array. Oh, it's just a array. So it's actually the notation shows it's just two one-dimensional arrays on top of each other. It's like one array. So it's just a row of arrays, an array of arrays. Woo, okay. I don't know where they got this name arrays. Just matrix. Okay, array, matrix, whatever, same thing. Just a row, grid. Okay, same stuff. So that's all it is. It's not just nothing special. And it's really funny. Okay, I just want to say this out loud that this in computer languages, this is confusing and this can really screw things up, is that they'll have row major and column major notation. So what I'm talking about here is like this int x, these two blocks here, says I want an array of arrays, which is, I want a matrix or a grid. But which is which is the column, which is the row? Well, it depends on the language. Yeah, so that's nice. So is 2 1? So in this one, this 2 is the first one. So this is going to be a row major, right? Because this is the first one is the row, and then the second one is the column. Other languages flip it. So just gotta be aware. Whatever your language is in, you gotta know which way it goes. Yeah, it's not confusing. And if you take code from one from another, and you got to make sure that this is flipped, because it'll totally mess everything up, obviously. So here's a string of characters. All a string of characters is just an array with usually a pointer to it, and it's just an array of characters. And those characters can be numbers, but it's interpreted as just a string of characters, not a number. It's interpreted as it's a string of characters. Now you could in your computer language, it can convert that string, if it is a number, to a number, actual integer, and back again. So we can get all that stuff going back and forth. But that's so you're stringing it in like a beads on a string. That's where they get it from. From back in the old days, the first one with this goes right back to this first day here. First thing is the string. Okay. All right. That's funny. It's for me. It's funny. Okay. So pointer, big idea. The value that represents the address of another location in memory. People make such a big deal about this. It's just a memory location, right? This one has 4, so it's got 4 in here. That goes I got to change this to 4 here. So this should be a 3 here. 0, 1, 2. Hold on here. Let me fix this one. All right, here we go. So I got this pointer here. Value that represents the address of another location memory. Okay, so we have an address here, 0. And in this scenario, there's only 1 byte at each address location. So it's going to have to get four addresses of all these 4 values, which is little. I guess this is going to be little endian, right? Because just zeros are first, and the 4 is last. So the little endian, it comes first. So and that points to this 0004 points to this address here, which has the value 2A. That's it. That's the major confusion. Oh my God, pointers. This diagram kind of messes up. So let me go look at this one over here. Pointers are so hard. So here it is. So the address 0 has value 4, right? Address 0, 0, 0, 0, 4, right? That points to address 4, which has a value of 2A, right? Or the ASCII character, or the ASCII character star, asterisk, or the star, people call it star, or the number 42, or the hex value 2A, or decimal 42 for base 10, numbers in our hands, or 2A in hex. And you put that OX at the beginning of it. It says, this is a hex number. Don't get it confused because, you can have it hex 22. That's not going to be the same as decimal 22. So that's why programmers always got to put this thing in the front, because if you don't, you're not going to know what if it's going to be you're interpreting these 2 digits as a hexadecimal number or as a decimal number. Oh, man, it's so much fun. All right, let's keep going. All right, so data structures or just structures or structs. They also say this. We can represent anything in memory as a structured list or more basic or primitive types. And here's some names. Get ready. Get ready for all the names, because programmers love data. Because we got a lot. So we got a lot. What humans love, we have lots of names of. Whatever we love, we just gotta have lots of names. Okay, so also known as records, data classes, data objects, data types, data models, data entities, classes. There goes okay. They're also called structs. Sometimes refers to classes interchangeably. Sometimes we call them objects and classes interchangeably, even though they're very different things. But programmers will switch back and forth and won't tell you. Classes to humans are very important. So we have, data to humans is very important. So we got lots of different names to the same basic idea exactly. Meaning as a standard. Okay, it has a standard format of possibly mixed types. It's so a struct is like a list of mixed types. So you might have characters, you might have a date, you might have just an integer, you might have a string, you might have some other bit code thing that's like a floating point or something, or the number of votes as a bit field. They call it just a bit field, like just a series of bits like that vote thing. Yeah, so like this here, like this. A bit field is this. This is just a bit field. Ooh, bit field. It's a bit field. Okay. Okay. So this structure can represent anything, any aspect of anything, right? Because we're not actually going to be able to ask it to have the actual thing in the computer. So we're going to be representing it, right? So like a person. What do you want to represent a person? Age, height, name, address, email. What are the things you want to track? What are you trying to track on the person? Is this like a database application for emails, for doing emails to people, or are we tracking some kind of scientific data? Do we need to know their collarbone length or their length of their teeth? What are you trying to track? Or animals or whatever. So it's really important that you're not having the actual thing. You're just representing pieces and parts of a thing that you call and put into the package called person in the particular system that you are designing. All right. It could be a house, a company, a country, a planet, a solar system, whatever. So keep in mind, it's a representation, not the actual thing. That's where we get a little confused sometimes when we say, it's just, okay, the person here goes there. Well, is it really a person? It's a representation of a person in this particular system, not the general thing. So that's where we get a little it's so confused. And that's called the classic garbage in, garbage out. So if we mistake the thing, if we mistake the actual thing, the map that we've given, the representation thing for the actual thing, there's a lot of problems that can happen. So it's really important to try and think about these solutions ahead of time, which you're actually doing. It's classic errors and very easy to do. So structure is usually made up of fields, which are individual pieces of data that make up the structure. Fields are also called properties, attributes, members, sometimes called elements. Different words for the same damn thing. It's a field. Okay, it's a field. I'm going to call it a field because that's what they started calling it before they called it all this other stuff. It's just a field. And, it's like having an outline. It's just a field in the outline. Fields are usually accessed by a name which is human readable label for the field. So it's just an offset into the structure of some data into the into the into this structure, which is a string of, as far as the computer cares, it's just a string of ones and zeros. But each one of those little sections means this means a number, this means a float, this means a string, this means a, you know, this means color, this means, you know, a vote for yes for give me a like on this channel. Fields can be different types like numbers, strings, dates, times, arrays, blah blah, or other programmer defined structs. So it can be other structures, and so you get this branching, you know, embeddedness thing. You can get very sophisticated. So here's a data structure in C. We've got a name here with 32 bytes. So we're gonna have maximum. The maximum we're gonna have for this system is gonna be 32 bytes. Are we sure that's the maximum? Should we do 64? 128? We don't know. We'll see. Okay. And the int, so we have the age. You can't be 2.5. You have to be 2 or 0 or 1. So what happens to your 6 months? Are you 0? Oh, do you have 2 months now? Oh, okay. And if you, okay, what happens next year? We have to go through all the database and increase everybody's age by 1? Do we have to record the birthday and record, or is this, okay, so these kinds of things come up. By the way, you should never store age in a database. You should always store a date or a time stamp of something, not the age. Classic errors. I've never done that. No. Here's a stack. Okay, so a lot of these things are these, like, you could play with these data structure visualizations here. Like, so let's just look at a stack here real quick. So a stack is just a way to represent the last in, first out line. So you have a list of things, and here's the first person that came, and here's the last person that came. And as a person comes in, it adds to the list. And as you serve people, they come off the front of the list. Or that's a queue, actually. That's the front. That's the next one. Sorry. So this is a stack. Is like, okay, you have a plate of things you put on first. And the last one you put in there is the first one you take off. And you can't go to the bottom. You can't go in the middle. It's only the top one. And it is used all over the place for all kinds of stuff. So you push something on the top, and that becomes the new top. You can't access anything in the bottom. You're not allowed to look. That's the rule of the stack. You can only see the top. And if you pop off the top, you keep the value. That's the last value that was popped off. And that the new top comes down to the next one on the list, and that one's no longer associated. That element is no longer associated with the list. That's a stack. And I wanted to say that there's all these different visualizations here, like a stack. So here's an array, right, of 30 values. So this is a stack implementation, a stack using an array. So it's implemented as an array, but it's a stack. Okay, so we'll push one on here. Push it on here. And okay, push one on. So let's do 39. We'll push another value on here. And so this is the array elements. This is array index 0, array index 1, array index 2. And the top is pointing to the next one. Now, sometimes in some implementations, the top will actually point to the last value. It really depends on the implementation. You'll have to look and find out which one it is. Let's do another one before we pop. So we push one more. It just goes out to the top of the stack. And then we pop. And the only one it'll pop is always the top. So you pop here. It always pops the top. Always pops the top. It never pops anything else. So that is a stack. And that's that. And here's, you can play some animations here, but it's basically just what I showed you. Now the queue is the one that's where it's like a line, where you have the head of the line and the tail of the line, and as you add new people as the time goes on here, you add to the head, and then as it comes along, it adds to the tail, actually. Well, add to the head. No, it depends on how it's implemented, but you're always adding things to the end of the line, right? To the tail, and then you're taking things off of the head, just like a queue, just like a line. And let's go look at it here, how it's implemented here. Let's look at queue as a linked list, which we'll get into the next one. So we're gonna get a little ahead of ourselves. That's okay. So the head is a pointer that points to the top node, the root node, and the tail points to the last node. And in this case, there's only one node, and it's pointing to both of them. So let's go to the next one. We'll call it enqueuing. We add it to the list. We add it to this queue. You enqueue it. This is 15 enqueue. So this is using something called linked list, which we're about to get into, which is just the pointers. So we have a value, and then it's another pointer that's associated with this node to the next thing in the list. And this has got a value, and it's got a point, and it's the next thing in the list. So this is a queue being implemented as a linked list. Put stuff in there. So this one's allowing me to put both numbers and strings. So it's basically it's just saving this as a string ultimately, because it's not creating, to save both numbers and the characters, you got to save the string. And so let's do DQ. So it's DQ comes off the top, off the head, adds it to the tail, takes it from the head. Just like a regular line. Just like a line when you line up anywhere. And then we DQ. And that's how that works. Let's see. So we just did the queue there. We can go play out. You can watch this animation. Here's the linked list. We just went through this. So the big idea is how do we represent a dynamic list? Instead of having an array of memory that's fixed, how can we have a list that has little memories, that has little pointers that point to each other? It seems a little dangerous, like they're all over the place. But it works great because the computer will remember everything perfectly. So we don't have to worry about pointers getting all mixed up. Now, when you're going to go work at this exercise, yeah, you might mess it up, which is part of learning how this stuff works. But in general, when I first encountered linked lists, I was like, that seems a little crazy. It's just pointers to the next thing. Can't they get corrupted in memory or lost? And it's like, no, they really don't. That's because I think I had a lot of problems with the hard disk because I just got a lot of crashes. For whatever reason, I just got unlucky with some of that stuff. That's why I learned how to do the backups so well. So I figured, if you just write these things to disk, it seems like it would be out of order. Well, it's like, and I had to think about it. It's like, well, I'm writing flat files to disk with just text, and that comes in most of the time okay. So if you had this linked list structure, it would do the same thing. It's like, okay. And then as I got used to working with them and seeing that they just work like everything else, it's nothing scary. It's no big deal. So it's a list of changing size are useful to organize because it just makes a memory use much more efficient when you can break things up into any area in memory. Because as memory gets used, it gets allocated and deallocated by applications. It can get broken up into different chunks, and having the ability to break up a list makes it more memory efficient. It also is really easy to change the size. So you're just adding another element as opposed to array. If you want to change the size of the array, you have to actually copy the entire array. So if it's got a lot of elements, that can take a while. Whereas a linked list, what takes a while is searching through the list for an element. That can take a while because you have the worst case scenario, you have to go all the way to the end. So it's an ON operation as opposed to an array, which is O1 because it's a flat contiguous. You can just measure an offset in the array and jump right to it. Whereas a linked list, you have to visit every single node along the list, which can take a while. Well, the computer actually does it really fast because it just gets the next one, just put. So it's super fast, but it still takes time if you got 100,000 or a million or 10 million of these things. It's going to be the lookup time is going to be an issue. But and that's where you might want to switch it to an array, right? And just do O1, boom. But it's going to take up all kinds of memory, so you're switching from time complexity to space complexity. Woo. So you're trading time for space for time. So there's in computers that you do that all the time. Like, okay, so this lookup thing's taking too long. Well, okay, so now we gotta put an array somewhere or make it into a table somewhere. And it's like instead of looking things up all the time and doing this really long lookup that takes ON, let's do O1 or or O log n. Somehow sort it somewhere, put it somewhere, and make it speed up. That's the best way is to do the naive implementation until it starts to become a problem. Then you go fix that. That's it's called premature optimization. Trying to do things the best way, most efficient way right out the gate. That is called premature optimization. It will totally screw you so hard. Don't be clever. Be real dumb. Be real naive and dumb when you first go into your problem. Just do it the dumbest way possible until it becomes a problem. Then try and do more complicated, interesting solutions to it that are more clever. But before that, don't mess with it. It's gonna ruin your life. Don't trust me on that one. Do much of that. Don't do it. I've done it, so it's a bad idea. Just work on it as you go. Okay, so the nodes are not a contiguous block of memory. It's the main difference between an array and a linked list. Just talk about that. The values are usually accessed by a pointer. So this is like the head. So this is first the head, but you have a pointer, a variable that points to this memory location. That then has this node has another pointer in it that points to the next one, to the next one, to the next one, to the next one, and then the tail points to the last one. Well, linked list sometimes will have a tail, not always. Sometimes it just has a head, and you have to run through it. Sometimes it'll have a tail, which makes it easy to add things to the end, right? And then the last pointer will point to null, or zero, or null, or void, zero, nothing. Meaning, in this case, it doesn't mean this go jump to zero memory location. It means that's the end of the list. You can tell you have a problem like on the old machines because if you didn't do this right and the end pointer was a zero, it would actually try and jump to that. You didn't set it up correctly. It'll use the whatever's at the memory location 0, which is who knows what's there. It'll go to another address someplace else, and it'll be like, okay, your program just crashed. You get this garbage result. Like, where is this? Why is this doing this? Oh, it's because I forgot to check for 0 for the null pointer. Oh, okay. So here's a map. So the big idea of the map is a way to represent mapping of keys to values in memory, like a lookup table, like the old timey phone book where you look somebody's name up and you get their phone number and address, or a business name and their phone number and address. And that's all it is. People make a huge big deal about this. Just look up. It's just look up. Here's the key. They call it the key. And then here's the value. This whole thing is the value. This is a JSON, a JavaScript notation. This is really used for a lot of times to save data because it's just human readable, right? You can look at, okay, there's the key, there's the value. It's not a bunch of hex codes. This was so crazy. Before JSON came along, it was just a bunch of hex codes. And everyone did their own style. It was such a nightmare. JSON just, even though it's goofy in a lot of ways, it's like over redundant, it's kind of like annoying in some ways. That's why I got adopted so readily, is because it was just a step up from the previous way. So there can be no duplicate keys. You can't have 2 gems. There's only be 1 gem, and it's always going to have 1 value. So I show you that's something special to know. Arrays can have duplicate values. Linked list, of course, all the other ones can have duplicate values. But one thing about the map is it is considered a set. So you can have 1 key to 1 value. Now you can have multiple keys you have different keys to the same value, but only 1 key to 1 value. That's how that works. The key is usually a string, but it could be literally any type, which is really odd to think about. You could be another data structure, and it takes that whole data structure, all the bits, and it does a little function on it, and it gets what's called the hash. It's like a unique value that kind of represents that whole data structure, the values in that data structure. That's how they kind of keep that. And you could use that as a key to something else. I don't recommend that. I've seen it in code. It is clever. It's some of the systems guys use it, but it's kind of, I don't know. I just rather have a string ID, some sort of identifier, like someone's name or an email address or some unique code that refers to it. Then that just makes more sense. Okay, so here's another map thing. So it's got the key, refers to, or points to, or maps to. Those are all the words we use. Maps to, points to, refers to the same thing. And then it points to a value. Key points to value. Key points to value. That's how that works. And if you want to see like implementation details, this video shows how all the hashing, which is just basically taking all the values of all the data structures, adding them up, just treating them as integers, adding it all up, running it through some function that gives a number, a special number, and that hash function is a special number. So that number that comes out of the hash function will always represent that particular set of values, and you can't. And if any bit in that set of values changes, the hash changes. So that's the unique. That's the idea of the hash. I'm not going to go into much more detail about that, but yeah, if you want to know how that works, it is useful to see how it works under the hood. But after you know how it works, you just use it. You don't care about it. And if you need to have a unique value of something, you get the hash of that object, and that's how you do it. All right, whatever. Tree. Big idea. It's a way to represent the hierarchical nodes, or a list of nodes in memory, which each node contains the values and points to one or more other nodes are just extents of the node. Okay, looks at a picture. Okay, here's your node. Pointer to another node. Pointer to another node. And that node can have a pointer to another node, a pointer to another node. This is called the left node. This is called the right node. This is an example of a binary tree. And in the also case of the binary tree, the left node, wherever the value is going to be less. So this node, the value here is going to be less than this node, and the value here is going to be more than that node. So it's for searching. And what does less more mean? Well, it depends on what you are hashing for the value here. If it's someone's name, first name, last name, you can search binary trees. The binary tree has to be sorted for that particular hash. But whatever it is, that's what you're sorting on. So that's how that works. Pretty straightforward. Like, it's not that super complicated. It's the same as a linked list, except instead of a linked list having one node, it has two. Ooh! Ooh! Well, there's like a bunch of mathematics you can do on this, which is, the searching stuff. But it's a linked list with two pointers. And then they have all the ones too. I think they call it a ternary tree. Guess how many pointers the ternary tree has? It's got 3. 3 and only 3. Right. So the binary tree will have 2 and only 2. Now both of them, one or both, could be null, but it'll only have 2. Only maximum 2, minimum 2, only 2. That's the binary tree. All right, and then we also have what's known as a directed graph, or another type of tree. This is a type of tree. This is actually the binary tree. So here's the root pointer to a node. This has a value of 50. So the right one, which is greater, 75, and the left one is 25. And then down here, oops, made a mistake here. It's flipped it for some reason. Let me go fix that real quick. Okay, I got that figured out. I'm using Mermaid, which we'll get into, just like declarative language to draw these using text. And it was acting strange, so I had to go edit it. Anyway, I got to figure it out. So notice that this is a tree, no cycles or loops. So this is also called a directed acyclic, meaning no cycles, not cycles, no cycles or loops in the graph. So this is a special type of graph that is easy for computers to traverse because it just goes down one and then the other and the other, and it goes. It's called. You can do the depth first search, where you go in there. You go down as far as you can, and then you keep going recursively up, down as far as you can, and recursively up, and then down as far as you can, and recursively up. That's called a depth first search. And then you have a breadth first, which it'll go to here, to this level, and then go this level, then this level, this level, this level, this level, and then this level, this level, this level, this level, this level, this level, and this level. That's called a breadth first search. So those are the two styles that you'll hear. That's all they mean. And here's the graph. Big idea. Represent a network. How to represent a network of nodes in memory, where each node contains a value and points to one or more, not just one or two. One is linked list, 2 is the tree. More than that, connected together, that allow cycles. This is the graph. So each one of these nodes can have one or more pointers to the other nodes, and you can see why having cycles makes it extremely difficult for an exhaustive search. This is just a few nodes here, and there's like at least a dozen different ways through to traverse from this one to this one to this one to this one, and this one ends up here. And what about from here? This one to this one to this one. Okay. What about from here to here? So how do you get to this one? There's no route. So you got to have some sort of mechanism that picks where you want to start the searching from for whatever reason, and so that becomes an issue. It's like how do you do that search? So Dijkstra has his algorithm for following paths and maps. So each one of these would be given a weight, right? How far it is away. Right now, these are all equal, so they're all equal weight of one, right? That'd be the Dijkstra way of thinking about it. And so you would have to figure out what's your strategy. Or, what are you trying to? Are you trying to like visit this one and then this one, or are you just trying to get shortest path from here to go, or do you have to go like through all the paths? It's the shortest way through all of them. Those are all somewhat unknown answers. And there are algorithms that do their best attempt, but there's no guarantees they'll do it in the time allotted, right? I'm sure you can find a way to get there, but finding that sometimes can take too long. So that's the end of data structures. We'll be getting into software next, which is the fun stuff. Yes, we're going to use all these little building blocks that we're learning to do more sophisticated stuff. That's why it's not really computers at this point. It's more like organization. Like, how do you set all these ideas up now? And we're not even really thinking about the machine very much, other than just an address and what the memory's doing, and our algorithms that we're designing. We don't really care what's underneath, honestly, and that's why you can get away with like these boot camps and places, college courses, get away with like not going into the deep stuff. Who's like, you don't really need to know that. Well, you don't after you know it. You don't need to know it after you know it, but it's useful as hell to know what the hell's going on underneath. All right, we'll see you next time.